Hello everyone, welcome to my channel. Today, let's discuss exterior differential informally. This is today's table of contents. Let's motivate the study of exterior differential by relativistic electromagnetism. We work in Minkowski space with coordinates x0 to x3. Note that we are going to distinguish the upper script and lower script and follow Einstein's notation throughout the note. We use HL units for simplicity, so epsilon naught, mu naught, and c naught are all 1. We set up some notations. For example, a vector field is a generalization of partial derivatives. For example, partial 0 means partial x0, and it can act on functions. For example, partial 0 act on f just means the partial derivative of f along x0. Similarly, we can define covector fields, and there is a pairing. For example, dx0 pair partial 0 is equal to 1. dx0 pair partial 1 is equal to 0. And we can even introduce a multilinear pairing. For example, we can introduce dx0 wedge dx1 pair partial 0 partial 1. This will give you 1. But if you pair in the reverse order, that is, if you pair with partial 1, partial 0, then you get negative 1. We deliberately choose the signs so as to define the corresponding electric potentials and magnetic potentials. Similarly, we will define the electric fields and magnetic fields. At this time, it is not clear why we choose the signs here, but it turns out that if we choose such sign convention, then the Maxwell equations, or more generally, the fundamental equations of electromagnetism, becomes easier to write down. Here, for the electric potential, we see that it is the sum of two parts. The first part is the time derivative of magnetic potential, and the second part is the gradient of the electric field, electric potential. For the second part, magnetic potential, it is simply its curl is the magnetic flux density. The third equation is the Faraday's law, and here we have the curl of the electric field is equal to negative the time derivative of the magnetic flux density. And there is no magnetic monopole. In other words, the divergence of the magnetic flux density is 0. So we would like to simplify all these equations. And therefore, we introduce the tool exterior derivative. Motivated by Hermann Grassmann's important but initially unrecognized work on exterior algebra in 1844, Elie Joseph Cartan developed this concept in 1899 to reformulate Pfaffion's system into an exterior differential system. Afterwards, this tool becomes useful in differential geometry and general relativity. We give some computational examples. For example, if mu is a zero covector field, i.e., it is just a smooth function with variables x0, x1, x2, and x3. Exterior differential d mu is a one covector field with the following components. And you immediately see that these components are similar to the components of the gradient vector field. We give a remark. We don't say that the exterior differential of a function is the same as its gradient here, because here we do not introduce a metric. It is out of the scope today. Afterwards, we define the exterior differential of a one covector field. What do we mean by a one covector field? It is just a linear combination of those dx0 to dx3, and the coefficients mu0 to mu3, they are just zero covector fields, i.e., they are smooth functions in terms of the variables x0 to x3. The exterior differential of this one covector field is a two covector field with the following components. Here I explained the notation a little bit. This bracket notation basically means pairing, and here d mu should be a two covector field. And as you expect from the expression of one covector field, it will be a linear combination of dx0 wedge dx1 and up to dx2 wedge dx3. There are 6 basis vectors of them, and if you pair partial 0 and partial 1, you basically take the coefficient of dx0 wedge dx1. So you will get partial 0 mu1, and you would like to anti-symmetrize this. I mean, unrigorously, this is sort of an anti-symmetrization. So you put negative partial 1 mu0 here, i.e. the pairing of d mu and the partial 0 partial 1. There are two derivatives. The first derivative is partial 0 mu 1, and the second derivative is negative partial 1 mu 0. Combine them together, you get the component for dx0 wedge dx1. And similarly, you have 6 components in total. Similarly, the exterior differential of a two covector field has 4 components, and for each component you get 3 partial derivatives. And you see that the indices are sort of a permutation of 012, 013, 023, and 123. And you see that there are different signs. This is sort of an anti-symmetrization, i.e., you check this permutation. You find that 1 is before 0. So this is an inverse pair. So you see that the number of such pairs is odd. So the sign should be negative. But here the number of such pairs is even. So you should have a plus sign. We will not state the general definition of exterior differential here, because it is very obvious if you already see the exterior differential of 0, 1, 2, 3 covector fields. Why don't we include the exterior differential of a 4 covector field? This is because we don't have enough basis vectors or basis covectors. This is a 4-dimensional space, so we have coordinates x0 to x4, x3. And if you compute the wedge product, you see that the wedge product is alternating. So you wedge you wedge 5 of them, you will always get 0. With the exterior differential defined above, it's possible to simplify Maxwell's equations to the following differential equations. The exterior differential of the potential 1 form is the field 2 form. And the exterior differential of the field 2 form is 0. Mathematically, we use a terminology called de Rham cochain complex to describe this. De Rham is a mathematician, and I think I don't need to explain this, but cochain complex is a homological object. That is, you have a chain of abelian groups, or you have a chain of vector spaces. Here you have a chain of vector spaces over R. You can also work with C, then you get the Dobout cohomology, but it's an overcomplication, so I won't introduce it here. And in addition to the spaces, you also get some maps. And strictly speaking, you should specify that this D is the exterior differential from C q minus 2 to C q minus 1, and this exterior differential is the exterior differential from C q minus 1 to CQ. But that's too clumsy, so we simply write D. And you have a chain of spaces as well as maps. And you cannot be too general here, because if too general, then it's not interesting. So they satisfy 4 axioms on the next page. The first axiom says that if you have a zero covector field, i.e., this is simply a smooth function in the variables x0 to x3, and you have an arbitrary one vector field. Note that this is a vector field, this is a covector field. There is a pairing between them, right? As long as they are of the same order. Yeah, if you take exterior differential with respect to mu, then you get a one covector field, and you can pair a one covector field with a one vector field. And the result, we assume that it is the directional derivative of mu along D. For all mu nu, for all p covector fields mu nu, they are of the same order, so we can add them, right? We can add them in terms of the coefficients. So we would like to require that this is linear. And for all p covector field mu and q covector field nu, in this case, they are not of the same order, so we cannot add them, but we can sort of multiply them. And in the Rham cohomology, the multiplication is given by this exterior product, or the wedge product. This product is different from the usual product in the sense that it is not commutative but alternating. So we should add a factor, -1 to the p's power, to sort of respond to that anti-commutativity. And this is very misleading, and sometimes people just make a lot of mistakes out of this factor. So we should be careful about this. And the last one is a topological requirement, that we require that for all mu for all p covector field mu, the double exterior derivative is 0. We call this axiom the exactness axiom, and you can really see this exactness axiom. For example, you take a zero covector field, say this is sort of a smooth function, right? And you differentiate it, you get something like this. This is sort of the gradient. And you differentiate that gradient again, you get the curl of the gradient. But the curl of the gradient is 0. And you generalize this to exterior differential, you get the exactness condition. we remark that a p covector field mu is closed if its exterior differential d mu vanishes, and is exact if it is the exterior differential of some p minus 1 covector field nu. In electromagnetism course, people usually don't distinguish this, especially when the course level is very low. And the reason is that the two concepts are actually equivalent if our domain is small enough. By small enough, I mean the domain is sort of a ball or a disk or something contractible. So according to the last axiom, a form is exact implies that the corresponding form is closed. But the converse is not true. It is a domain issue. For example, you can take the argument form, right? Integrate this, you will get the argument. And this is used in complex analysis a lot. And also, you can sort of take your green functions for Laplace operators, and then you differentiate it, you will get 0. But if you try to find an antiderivative, you see that it is impossible, because the integral of the Green's function on a sphere is actually a positive constant if the sphere contains the singular point. So the relative relation between the set of all closed forms and the set of all exact forms is important. So we simply define the quotient of closed form over exact form as the pth de Rham cohomology of the space. As a remark, this is the letter Z, stands for cocycle, and this is the letter B, stands for coboundary, and this is the letter H, stands for cohomology. And we have already described the essential material for exterior derivative alone, but we are going to relate it with an important structure, and I choose not to relate it with metric, because if I relate it with metric, then this note becomes a bookwork, right? It becomes a bookwork on Hodge identities, and you're going to find that there are many conventions of the of these Hodge identities, and then this is not so interesting. We introduce a seldomly introduced concept in the course Mathematical Methods for Physics. That is, we sort of relate another structure, that is the Lie bracket of vector fields, together with the exterior differential. Consider two one-vector fields on R2. One-vector fields, if you recall, it is a linear combination of those partial derivative operators, or you can say it is the standard coordinate one-vector field, but this is just a tautology. This is essentially some differential operators, ddx0, and you do linear combination. I choose R2 because if I choose R2, then the relation is simple enough to describe. Their Lie bracket, i.e., I measure the non-commutativity of these two differential operators. For example, if you imagine D is the position operator, although you should not do this, because in this case the position operator is not a differential operator, but you can sort of imagine that. So you use these D and E to act on the state vectors, and you measure the non-commutativity, you get the Lie bracket. And you want to compute this Lie bracket in terms of coordinates. So you pair it with a standard basis covector. You will get these anti-symmetric relations. This construction actually works in general, and as a remark, these mathematicians usually describe it as a natural family of transformations, but it's not that important here because this is an informal discussion. And thus, this turns the set of all one-vector fields into an algebraic structure in quantum mechanics that describes the relations between Hermitian operators, i.e. Lie algebra. We observe that exterior differential and Lie brackets are related via pairing. So we introduce another core material for today's talk, that is the relation between exterior differential and Lie brackets. For every one covector field mu and one vector field dE, we recall that the exterior differential of mu is actually a 2 covector field. So it is a linear combination of the terms like dx0 wedge dx1, dx0 wedge dx2, dx2 wedge dx3, and so on. And the coefficients are given by two partial derivatives because it is sort of a curl-like expression. This is a one covector field, so you expect that the result is similar to the curl of something. Now you get a two covector field. You are going to pair them with two one vector fields. Note that this terminology is confusing. I take two vector fields and both of them has order 1. And now you have a pairing. And if you compute this by brute force, you will find that it is actually equal to d act on the smooth function mu pairs e minus e act on the smooth function mu pairs d, and minus the pairing mu with the Lie bracket of d and e. For each well-studied Lie algebra in physics, the relation above induces a de Rham cochain complex. We add some quotations here. So this is because technically we shall introduce more subtle terminologies. But this talk is supposed to be informal, so we don't do this and identify everything. This is related to BRST cohomology and the gauge theory. As an example, we sort of introduce some very famous and very well-studied Lie algebras in physics, and we construct the cochain complex. The spin of electron is described by the one-vector fields, and you should recall that J minus and J plus are ladder operators, and J3 is a Hermitian operator measuring the third component of the angular momentum. And now you have some commutation rules, right? But you should be careful that none of these lie in the Lie algebra. Actually, the Lie algebra of SU2 is the set of traceless and skew Hermitian matrices. So none of these satisfy this requirement. Nevertheless, they are simpler than the standard basis J1, J2, J3, and you multiply them by I. This will be simpler, so we work with them. Their Lie brackets are given by the following table, and we would like to find a cochain complex. So we should recall that for a cochain complex, there is a co before this chain complex. So this means we should take the one covector fields. And you notice that the indices are carefully written. So this minus, this plus, and this 3 are lower indices. So they are one vector fields. You raise them to superscripts, you get covector fields. And by covector fields, I simply means that J minus paired with J minus is 1. J minus paired with J3 is 0, and so on and so forth. So you can deduce the structure equations of SU23. We explain the details. The details is like you take your mu, or you take your mu to be J superscript, and you take D and E to be J lower script. So you see that the pairing mu, or the pairing mu D and the pairing mu E are both constants, right? So they are either 0 or 1. This doesn't matter because if you differentiate the constant, you will get 0. So the first two terms are 0. And the only interesting term is negative the pairing of mu with the commutator. So you can use this table to compute the exterior differential of those covector fields. Using this covector, using this, you can deduce the entire cochain complex. For example, here, suppose that we are going to compute the exterior differential of J minus wedge J plus. This is a 2 covector field, and when you differentiate it, you expect that you need to do it on the first entry and do it on the second entry. But recall that there is a confusing part. That is, if you differentiate on the first entry, then the sign is plus, there is no problem. But if you differentiate on the second entry, recall that J minus is a 1 vector field, so there is a negative 1 to the first power. So actually the rule is D bracket J minus wedge J plus is equal to dj minus wedge J plus minus J minus wedge dj plus. So you should be careful in doing this. And if you compute all those B, Z, and H, you will find that the Ram cohomology groups, also the remark is that they are not really the Ram cohomology group, but they actually coincide. I just write down the non-zero ones. The zeros, the Ram cohomology group is R, and the third Ram cohomology group is also R. The zeros cohomology group corresponds to the number of connected components, and the third Ram cohomology group corresponds to the fact that your group SU2C is topologically a 3-sphere, which is desired. So finally, we apply this theory to the color charge generators. Recall that the color charge of quarks is described by the 8 linear operators, where you see that the upper 3x3 block, or the first 3 operators, T minus, T plus, and T3, they are the T-spins of these quarks. And U minus U plus, V minus V plus are some ladder operators, and Y star is the hypercharge. I add this star simply because I want to distinguish the one vector field Y and the one covector field Y star. This will be useful if I'm going to compute the exterior differential of these covector fields. And you see that the Lie brackets are indeed very messy, but but they are computable. If you use a computer, then you can compute them in seconds. So mimic the same procedure here. You get the structure equations of SU3C. And in principle, you can use this to compute the cohomology of SU3. And if you do this, you will find that the cohomology groups are R for H0, H3, H5, and H8. But be careful that for this vector space or this Lie algebra, it is 8-dimensional over R. So if you compute the exterior powers, you will get the binomial coefficients 1, 8, 25, 28, 56, 70, and so on as their dimensions. So you don't want to compute a 70 by 70 matrix by hand or by computer. It will be very slow, right? So actually, the standard way of computing this cohomology is not like this. We should use other tools to compute these cohomologies effectively. For example, the fiber bundles. But anyway, I'm just introducing the interesting relation between exterior differential and Lie brackets here. So this matches the standard fact in algebraic topology, where the cohomology of this SU3C is given below. And this is the end of today's talk. Thank you for listening.